Fast race for Bandit's optimization with UpperConfidence, Frank-Wolfe.
Thank you very much, Philippe. Thanks for the invitation as well. It's a great pleasure to speak in such a cool workshop. So today I'm going to talk about generalization of multi-arm bandit problems and one way to solve this problem. I should say that this is joint work with Berthet, and I should also say that he's the one who sent me this picture. Okay, so since this is a generalization of multi-arm bandits, I'm just going to start by recalling what this means, at least from our point of view. So we're going to consider the stochastic case. And so this means that at every round, you choose one of k actions. So in a casino, this can be slot machines or one-arm bandit, hence the name of the problem. And each of these actions is associated to a distribution nu I with some unknown mean mu I. Okay, and the principle of the bandit feedback is that when you play one slot machine, you only observe the feedback from this slot machine. So you observe the feedback drawn from the distribution nu of pi t when your choice is a policy pi t in between 1 to k, right, with mean loss mu of pi t. So of course, the idea is to minimize the cumulative loss or its expectation, right? You want to lose as little money as possible in a casino. And so if you take the average, it's equal to this, or if you take the expectation, if you take the corresponding means, you get something like this. And then one point of view is that this can be treated as a stochastic optimization problem, right? Of course, you don't know the mu's. If you knew them in advance, you would just always pick the action that corresponds to the smallest loss. But if you don't, the idea is that you can rewrite this function in this way, right? So if you don't sum over time, but sum over all the actions, this is equal to mu I times the number of times you've played action I. And since you're taking an average, you can write it like this as well, right? Ti over t. Right, so if you look at this variable, this is vector in the simplex, in the unit simplex, and you can write your loss in the multi-arm bandit case as just a linear form like this on the simplex. Right? And so now you can see the multi-arm bandit problem as a stochastic optimization problem where you try to minimize linear form on the simplex with an unknown vector. Okay? And so you have this picture. The minimum is here. This would be the best arm. You can measure your pseudo regret. This would be equivalent to an optimization error in this case, right? And the important thing is that the feedback that you get on the unknown mu is tied to this variable pt, right? So it's not like in stochastic optimization in general, where maybe you get independent gradients at every step, independent information on the whole vector mu. If you never play this action, and so the variable is always here, you only know about the variations of the functions on this line. You never know about how much it varies here. Right? So if you're playing this game here, this could be really bad because this means that you would never know anything about the fact that in order to minimize it, you need to go downhill. You need to go there. Okay, so there's really a link here between, in all these bandit problems, between what you play and what you know about the function. Okay? And so in this case, the associated optimization problem is very simple. There's one best action, and this is the action that you should always play. But in a lot of situations, let's say you're going into a supermarket, your utility function is not linear. There's not one best product, and you should not fill your basket only with this product, right? And there's many other applications like this, right? So going with the supermarket example, imagine that there are k goods in a supermarket, and your objective is to maximize some unknown utility function. Let's say it has some unknown parameters beta I, so this is known as the Cobb-Douglas utility function. And you can rewrite it. As equivalently minimizing some loss on the simplex by taking this loss. Okay, and so the idea is that every time you put something in your basket, you have some, looking at your basket, some evaluation of how much more happy you are with this item in your basket, and so you observe some noisy change in utility with mean beta of pi t, right, where pi t is equal to some I, right, for only one of those, for only the object that you put in your basket. Right, so now this becomes a different stochastic optimization problem, still on the same variable, but with a different function. And now the optimum is not going to be in a corner, it's somewhere in the middle of the simplex. Right? If you knew the beta i's in advance, you could compute that it's equal to that. But if you don't know at all the beta i's, or don't even know that your utility function looks like this, you only see some noisy change in utility, then the question is, how can you fill your basket optimally with only this noisy feedback? And again, here the information on beta is linked to the variable pt. Right? If you never buy one of these products, you never know about beta. Okay. So this is now what the corresponding picture would look like. This function is not a linear form anymore. The minimum is somewhere in the middle. And this is a simple example for a problem where you don't have one optimal action, but there's an optimal strategy that's just optimal weighting of all the actions. And then again, now this is a stochastic optimization problem with a convex function on the simplex with some unknown beta. Right? And so there are many other ways to see applications of these types of a problem like this. The one that first brought me to this was linked to statistics. The idea is that you're trying to estimate some unknown vector theta, and you have k sources that correspond to each of the coefficients, and they each have a different variance sigma I square. Okay, so now if you have first-year undergrads, you can ask them what's going to be the expectation of the loss of the very simple estimator, and you'll find it's equal to this. If you have second-year undergrads, you can ask them to find the optimal TI so that you minimize this error. They will find that the optimal TI are proportional to sigma I. Right? If there's a bad source, this means you should sample more from this source. And so this is equivalent to minimizing a loss function of this type. There are other problems, sequential resource allocation, your government sending teachers in one region, and you get a noisy feedback of whether or not there's less, or you should send more or less teachers in that region. So you can phrase a lot of optimization problems like this, where you have an unknown function L on the simplex, and it's unknown because it has some unknown parameter, vector parameter with one coefficient associated to each action. And the feedback on the parameter is tied to the variable pt. Right? If you've played some action a lot of times, this means that your estimation of this particular coefficient is more accurate. And again, you have some optimum p star somewhere in the simplex, and you have some optimization error that looks like this. Okay, so to formalize all of this, now that I've given a bit of motivation, the problem is that you have an unknown convex function L on the simplex. At each round, you must choose one action, and only one. And at each round, you're observing a vector, gt, which is a proxy of the gradient. The idea is that the ith coefficient of gt is going to be an estimate of the ith coefficient of the gradient with a precision that depends on the number of times that you've played the action I so far. Right? This is this capital Ti of t. Right? So this doesn't come from, out of a hat. This is motivated by all these parametric settings. And so the objective, of course, is to choose your actions in order to minimize this loss. And the performance of any policy, because there's randomness, it's going to be measured by the expectation of L of pt compared to the minimum. Right? Are there any questions about the setup and the problem? Okay. So the natural question is, how do you solve this? No, there's one. Before that, there's a comparison review. So the idea is, how is this different from Bandit problems? First, it's a little bit different because the loss is not cumulative. Right? You're not looking at an average of losses at each action. You're looking at the loss at the average of all the actions. Right? So there's no natural notion of regret here. Again, there's no individual best action. If you have a natural notion of regret, there's one best action. Here, it's not the case. There's an optimal mixed strategy. And how is this different from stochastic optimization? Well, it's different because you can't choose a new variable xt at each round. It's linked to all your actions before that. This is this vector pt of proportions of each action, and it cannot be chosen freely in your domain. And the gradient feedback that you're getting is also tied to these actions. It's not independent stochastic. So really, you have a lot of constraints on this stochastic optimization problem. There's existing work that is a bit similar to this, where there are linear bandit problems with non-convex loss, but it's a little bit less general. So again, the take-home message of this problem is that you have the rules of bandit problems when trying to do stochastic optimization, right? So it's a little bit more constrained. Okay, so how do we approach this? How do we try to solve this problem? The idea first is that when you write just a dynamic of the problem, right, just looking again at the rules of the game, what happens when you choose a next action at time t+1, you have this equation for how your point is going to move, right? So this is just writing the definition of pt and pt+1. And when we first wrote this, we thought, okay, this looks a lot like some sort of gradient type update, right, where you're doing a step in one particular direction. And in particular, because now this point is a corner of the simplex, it looks a lot like a Frank-Wolfe type update. Right? So the Frank-Wolfe algorithm is a type of algorithm to minimize convex functions on convex sets with nice extreme points. The idea is not to step in the direction of minus the gradient, but to find the extreme point that's the most in the direction of the gradient, right, by solving this linear problem, and then to step in that direction, right? So to take a convex combination of xt and ct+1. Right, so here, if this were known in advance, right, so if we knew the loss function, we would have, Frank-Wolfe would just tell us, well, this is the new action that you should take. You know the gradient, so you should take the extreme point that's the most going to be in the direction of minus the gradient of LP. And the big issue is, of course, here that we don't know L, right? So in this case, we would just do this. In this case, we just do this with this step size, which would just mean taking the I such that the ith coefficient of the gradient is minimum. And for a C-smooth convex function, we would get a guarantee of this type, right? We'd get a convergence of order log t over t. So now, if we have an unknown function, but we have some sort of stochastic gradient instead of having the gradient as an information, the first idea is to just plug in the stochastic gradient in this problem. So now, of course, people familiar with multi-arm bandits already know that even if this is a linear function, this is a horrible idea. The issue is that if you always take the action that you think is the best right now, you might be very unlucky on the best action in the beginning, and so this means that you're never going to pick it again, and so you're going to have horrible rates of convergence. It's not going to go to 0. So the usual fix in multi-arm bandit is to correct for uncertainty. You don't look only at the gradient that you have, but you look also at the set of statistically feasible gradients in some sense. Right? So you take into account the uncertainty, so you take a valid confidence interval or region for any coefficient. And in the case of multi-arm bandit, so the gradient is just going to be mu, and the estimate of the gradient is just going to be this vector of estimated mu hat. And so you just correct by the size of the confidence interval, right? So this is like taking the estimated vector and adding a vector of uncertainty. Right? And you solve this, and since 2002, we know that this has some really nice performance. Okay, so our idea was, well, to do this and to generalize it to a Frank-Wolfe algorithm. Right? So to take a Frank-Wolfe algorithm and to update and to plug in not only the estimated gradient that we have, but an estimated gradient corrected for uncertainty. Okay, so this is the upper confidence Frank-Wolfe algorithm. The idea is that at each round we observe this noisy estimate of the gradient. We correct for uncertainty, so this should be Ti of little t. And then we select the action such that the coefficient of this vector is the lowest, right? So we're not only guided by the gradient, we're also guided by the uncertainty. The idea is that here we want to promote exploration. Yeah.
So if I'm looking at this is making the assumption that the gradients are bounded in between 0 and 1?
No.
But then how is this an actual confidence bound for U hat?
No, we have like some variance 1. This is the assumption that, so we have some assumption.
The gradients are sub-Gaussian.
Yeah, we have some assumption that we have some noise.
So how does, so early on you motivated some of this by using the example of utilities, t to the power beta I,
yeah.
And you said your loss was beta log p.
Yeah.
Log p's derivatives.
No, so this is not an uncertainty on p, this is an uncertainty on beta, right? So the idea is, in this example, let's say you get some noisy estimate of beta at every time. This is motivated by the change in the log of the utility. But so in the paper, we have cases where it's not only sub-Gaussian, like any kind of really generic decreasing function. Here I'm just presenting the natural case when it's 1 over square root of Ti.
Okay.
So here the assumption is that really this is a valid confidence interval. That's like in the description of the problem. And so yeah, so we're promoting exploration by adding this. If we omit gradient computations, this is very simple. At every round, we just need to update our vector, compute new confidence intervals, and then just take the lowest of these coefficients. And then the update is just happening naturally. And so the proof elements for this link elements from convex optimization and some elements of the proof for UCB. Okay, so I'm just going to go quickly over this. The idea is that if we just take the proof of the Frank-Wolfe algorithm with known gradients and a C-smooth function and we adapt it, the idea is that we are going to obtain an error which has the optimization term and also a term of errors, right? So this is just the error of choice, the fact that you haven't chosen you haven't actually chosen some action that's the action that the Frank-Wolfe algorithm would tell you to do. Right, so in the multi-arm bandit case, this is just the difference between the two means, the one that you've selected and the best one. And in general, this is less than the coefficient of the gradient that you've chosen minus the actual lowest coefficient. Right, so this is really the difference between what you would have done if you knew the gradient and knew what you have done instead. Okay, so similarly, adapting the proof of the UCB algorithm for multi-arm bandit, we obtain the slow rate. Under very general condition here, we're just assuming that the function is convex and C-smooth, right? So we have statistical term that dominates, and we have something in square root of log t over t. Okay, so in the linear case, if the function is linear, this matches the result of UCB. So, and actually the algorithm is the UCB algorithm. So this is just a Frank-Wolfe type proof of the rate of the UCB algorithm. And up to logarithmic terms, it matches the actual lower bound in this problem. Okay. So now if we make some small improvements by adding some conditions and looking at instance-dependent rates, we can get faster rates. So in multi-arm bandits, that's already known. If you have gaps between the smallest loss and the losses of other actions that are bounded away from 0, you can improve this to a fast rate, something in 1 over t times something that's dependent on the gaps. If this goes to 0, it will blow up, but if it's bounded away from 0, that's fine. The idea is you just do some simple algebraic manipulation based on Cauchy-Schwarz inequality because you're bounding initially the number of times you've played the wrong actions. The idea is that the general lower bound is built on a case where you have this type of gap. So this is a situation where the function is flat enough, maybe between 2 points, so that you're statistically confused between these 2 points, and at the same time, the difference is large enough that this is actually causing you a problem of order 1 over square root t. And it also has a nice geometric interpretation in the simplex corner. This is just saying that minus the gradient is going in this cone in the corner of the simplex. The KKT conditions are already telling you that this is going to be non-negative, but how it is bounded away from 0, how the deltas are bounded away from 0, describes how deep this negative gradient is in the corner. Okay, and so we can extend this to cases where the loss function is minimized in a corner and where we have gaps on the coefficients of the gradient. Right, so by doing essentially the same proof, except here that this is an approximation, not an equality, we have this type of result. And you can see that as the function gets flatter and flatter, and the negative gradient gets closer to the boundary, this means that this is more and more easy to hesitate between these two corners. That's the geometric interpretation. Okay, so we have fast rates if we make additional assumptions, but this will be only for now. In cases where we are in a corner, right, when there is one optimal action and this is the one that you should choose. But in the beginning, I spent all this time explaining that what we're actually interested in are situations where there's one optimal mixed strategy that's in the inside of the simplex. Right? And the idea is that if the function is allowed to be very flat, that's going to be a problem. So we look at what happens if the function is not allowed to be flat anymore. We consider mu strongly convex functions, right? So there's always a quadratic term in this inequality, and cases where the minimum is bounded away from the boundary of the simplex by some parameter eta, right? So this is just saying essentially that we leave some room around the minimum for this inequality to make sense, to be usable. This is a very classical hypothesis in stochastic optimization and also in the analysis of Frank-Wolfe. So there's many other people than this who've looked at that. But usually in bandit-type problems, more classical bandit-type problems, this is not always exploitable. And so we didn't know initially if this was going to be exploitable, if we're going to get faster rates in this problem. It turns out that it is actually possible. The idea is that there's a convexity bound that we're using everywhere in our proof that can be improved under conditions where you have strong convexity and the minimum is bounded away from the boundary. So this is a lemma from Lacoste, Jr. and Yagi that's hidden in their paper but very useful. And from this we can get fast rate for mu strongly convex function with interior minimum with the same algorithm. We're not telling the algorithm that the function is strongly convex. The two-line proof idea that takes more than 20 pages is that essentially these are the epsilon t's. And so now if you replace them, if you replace the inequality by a square, you have something that looks more like this if the epsilon t's are decaying fast enough. And the slow rate initially already implies that you're already using each action more or less up to some square root the appropriate number of times. So the precision, because it decays like 1 over square root of ti, decays also like 1 over square root of t, and so essentially it works. And you have squares, which means you have a 1 over t instead of having a 1 square root t.
Is there an assumption that t is larger than k or something?
Yeah, so I think this is for t large enough and k is fixed in our setting. So we look a little bit at the dependency in k. But yeah, you have to be able to play everyone at least once.
Is it poly k or it's k or it's...
Linear in k. Yeah, but we haven't optimized this, so yeah, I'm not exactly sure. So the summary is that in general, for only C-smooth functions, these are the results that you get. If you make an additional assumption, because this is optimal, so either a corner condition or, which is something that's a little bit more suited to our setting, a strong convexity with interior minimum assumption, you can get faster rates. So in the first case, this is optimal up to log terms with linear forms, and in this case as well. now the question is this optimal as well? So the answer is, again, yes, up to log terms. And this is done by looking at a family of functions, so quadratic forms that are minimized at a point that's close to the minimum. And we look at a lot of these functions. And we show that in our model, it's going to be hard to distinguish between any of these functions based on the observations, which means that it's hard to optimize. Right? This is the classical way of doing lower bounds in stochastic optimization. If you could optimize your functions, it means that you could solve a statistical problem well, and in this case, there's a lower bound. So it leads to a lower bound of this type, which you can compare with our upper bound. So initially, this was a bit worrying to me because it looked like our upper bound was beating the lower bound. And what I realized is that actually, this is not a parameter like 1/2. This is the distance away from the boundary, and in the simplex, this needs to be smaller than 1/k, right? So actually, we realized that we have a pretty bad dependency on k, and this is something that we could optimize. Something else is that in our setting, we have a direct link between action and observation, right? So if you play action I, you observe something about the ith parameter. Natural question is, can this be relaxed to a mixed bandit feedback? This would be in particular interesting in adaptive sampling and experiment designs. In general, if you make no assumption, this can be pathologically bad even in dimension 3. The idea is that even for strongly convex functions, you can look at a function of this type where in order to optimize the first term, you need to know theta well. And the only way to get information about theta is to play the third action. And so in this case, very naturally, you can show that you get a lower bound of 1/t to the 2/3, which is much worse than t. I think still that this is an interesting question, and I think that if you make additional assumptions, such as you're learning from the parameter I a little bit, at least when you're playing action I. The way to learn about parameter I is not only to play other actions. I think that this can be improved. Okay, and so to conclude, this is a new model that links stochastic optimization and bandit problems, generalizing multi-arm bandit. I think that it's a natural playground for a lot of applications and to consider other types of problems, such as online experiment design. And also what I liked was the solution was bridging these two domains, that we're using ideas from the two domains, and the proof also was just using ideas from these two domains, and that we get adaptive fast reads. So there's ways to design algorithms that would work well in a lot of these other conditions, but this works well for everything without knowing essentially anything about the function. There's lots of open questions. If you're interested in this, or if you think you have ideas about this, I'm very interested in talking to you. And I guess everyone's looking forward to lunch, so I'm just going to end here. Thanks a lot.
Questions?
Can you get first order regret bound where the regret depends on L star rather than T?
On
the regret is like L minus L star is bounded by something.
Yes.
You would like this something to be smaller than L star. Saying that.
Oh, like multiplicative type.
Yeah.
We haven't considered that, but I think it would be possible because essentially these types of bounds exist for Frank-Wolfe, and so I think if you just translate that into this theory, I think this would work as well. I'm not absolutely sure, but we haven't thought about it.
So I have a question. Can you, so here you had, I guess it was motivated by the parametric assumptions that you always have the same confidence no matter where you actually query your gradient.
Yes.
And
okay, yeah.
is it possible to extend it where this would actually change? And you can think of setups where this is actually would be the case?
So for the first question, I think it's possible to change it. So we've considered just general functions. We've considered general functions where you can change the way it depends on ti. But what you're asking is actually this, right? If it depends on the whole trajectory.
If it depends on p.
Yeah. So we've thought about this a little bit, but we haven't pushed it because, so to answer your second question, we're not able to think of motivations for this.
All right, so the bells tell us that it's lunchtime, so we'll see each other in 2 hours.